So hello and welcome to April's Plum Tree, and I've got Plum Tree Village Hall behind me, just to remind us all what it looks like, and hopefully we'll get back there soon. So April 2021, tonight is myself and Leigh. We're going to talk about aberrations, artifacts and other optical issues in amateur astronomy. I bet you're all glued to your seats. So I'm going to go on first and then Leigh. So there's an extensive list of different sorts of aberrations and artifacts in amateur astronomy. And we're just going to discuss some of the commoner ones. Those with specific interest in optics will probably be bored by this evening's talk, and will know of many more aberrations than either myself or Leigh do. So we're going to talk about the commoner ones and steps that can be taken to resolve, or if they can't be resolved, then just an acknowledgement of maybe you have to live with some of them. Now I'm going to talk predominantly about things relating to optics and visual astronomy, and Leigh will talk about things mostly relating to astrophotography. It's not an easy line between the two, so there's a bit of crossover, but we've tried to keep it that way. So here we go, optical aberrations in amateur astronomy and other things which can make observing more difficult. An aberration, the definition is a departure from what is normal, usual or expected, and it's typically something which is unwelcome. In optics, in particular, because that's what we're interested in, it's defined commonly as the failure of light rays to converge at one focus because of a defect in the mirror or the lens. Now, for us tonight, that definition isn't strictly correct, as some of these aberrations occur even with perfect optics, so there's no defect, and some of them occur even when the light rays are focusing correctly or converging. So I'm going to talk about, use some simple illustrations. This is a simple illustration of, let me put my laser pointer on. So this curve is a simple curved spherical mirror representation. And it's important to say tonight I'm going to show both mirrors and lenses and use them interchangeably because they both have very similar effects on light rays. They both bring them to a focus, or certainly a curved mirror will, and a lens will bring light rays to a focus. So we will use them interchangeably. So in an ideal system, we have a mirror in this situation, and we've got a distant star, and the light from the star is coming in through space, through the atmosphere, and being collected by our telescope, hitting the mirror, and is being brought to a focus. And so here we've got the light rays coming in, reflecting off the mirror, and they're reflecting uniformly, and this will be the focal point at the focal plane. And in a Newtonian telescope, there would be a secondary mirror here, which would send the light rays out to the side. If this was a Schmidt-Cassegrain, there would be a secondary here as well, and it would send the light rays back through a hole in the primary. But the principle is the same, that the parallel rays of light are coming in and being brought to a focus. And what happens is wherever these rays are coming from on the object, ideally all these rays are brought to the same focus, so everything is nice and sharp for the observer. So the first aberration we're going to think about is spherical aberration. So I said earlier that this is a mirror, so we're going to assume now this is a simple spherical mirror. So if you imagine a football, we've cut a football in half, and we're using the inside of half of that football to cast a mirror, and so it will be a hemispherical mirror. Now, spherical aberration predominantly affects reflecting telescopes. There'll always be some caveat about these aberrations and them having different effects on different types of telescopes, but this is predominantly a reflecting telescope problem. And what happens here, again, we've got light coming in from a distant star. Light waves are all traveling parallel, and the red isn't representative of red light, it's just different rays of light coming from the star. And the red rays are brought nicely to a focus, but because this is a spherical mirror, rays at different parts on the mirror will be brought to a focus at a different place. So you can see the red rays here are brought to focus, and that is where our focal plane is, so they'll be nice and sharp for the observer. But these rays lower down, because they're reflecting off a different part of this spherical mirror, are being brought to focus at a very slightly different place. So at the focal plane, which will sit here, these black rays will be out of focus, and they haven't yet reached focus, so they'll be slightly bigger. And what we see is this kind of artifact. So you see concentric circles, concentric rings. So we've got those red rays have formed a nice focal point or spot in the center, and then other rays that are hitting that spherical mirror are being on the focal plane, they're not achieving focus, so you get this concentric pattern. And what we can do is we're going to now think about parabolic mirrors. So remember I said a spherical mirror is like a football cut in half, and the angle is the same throughout that mirror. But a parabolic mirror, this is a grossly exaggerated impression of one, is not a spherical mirror. We need to think about parabolas and things at a future date. But what happens with parabolic mirrors, as long as the rays are coming in on the main axis of the mirror, it doesn't matter where they're hitting this parabolic mirror, they're all being brought to focus at the same point. So with parabolic mirrors, we don't get this spherical aberration, and most mirrors in commercially available reflecting telescopes, like Newtonians, today are made with parabolic mirrors to avoid this problem of spherical aberration. Some cheaper telescopes still have spherical mirrors. Here we go. Yeah, have spherical mirrors, but the manufacturers put some glass in the focus tube to partially correct that, and that's called a Bird-Jones or Jones-Bird reflector. And generally these are much cheaper instruments and give less enjoyable views of the night sky. So how we can resolve spherical aberrations is don't use spherical mirrors or spherical lenses, use parabolic ones. And so we've seen that the modern Newtonians will have a parabolic mirror, so it's not usually a problem. Now, Schmidt-Cassegrain's, the primary mirror in a Schmidt-Cassegrain is actually a spherical mirror, because it's cheaper and easier to make, but the glass corrector plate at the front actually goes a long way to correcting the spherical aberration. So there isn't any spherical aberration in an SCT, even though it has a spherical mirror. As I say, it's now an uncommon problem for most telescopes. Now, the next thing we're going to think about is chromatic aberration. So chrome color aberration, and this does relate to color. It's mostly a problem with refracting telescopes, and so here we've got a simple lens in cross section. So you imagine we've got a star out to the left emitting light, and that's coming to our telescope, going through this lens, and the lens is bringing the light rays to a focus. And again, we imagine this is the focal plane, and this is where the observer will view, and it's in this situation it's nice and sharp, and the observer's happy. But what happens with lenses, and you know about Isaac Newton and putting sunlight, white light into a lens, a prism, and it breaks it up into the component parts, the different wavelengths, the different colors. And that's exactly what a simple lens will do. It'll break up the starlight, which is effectively white light, into different parts. And now these colors do represent the different wavelengths of light. So we saw previously the focal plane was here, and the blue light's been brought to focus nicely. But here the red wavelengths are refracted, they're bent less than the blue ones. So even at the focal plane, the red light hasn't yet achieved focus, so it's out of focus. And this is what chromatic aberration is. It's a failure of the system, the lens, to bring different wavelengths to the same focus. Now, we've got here an image I took of the Dumbbell Nebula, and you can see the stars are different colours. There's sort of yellow ones and bluer ones and white ones. It's not a stunningly good image, but it serves a purpose here. Now, what happens if there was chromatic aberration in this picture? You can see, this is the version with chromatic aberration, you can see there's a difference. So go back to the nice image with no chromatic aberration, and then we add in some chromatic aberration, and you can see the stars are losing definition, and there's something wrong with them. And what we're going to do is zoom in. So this is on the nice image. You can see the stars, orange stars, bluey white ones. They all look quite nice. Now, if we zoom in on the chromatic aberration one, this is again a false generated image, but it helps to show the principle. We can see that those stars now consist of a green dot, a blue dot, and a red dot. And if we look even closer, you can see that here. It's like the pixels on an old-fashioned TV. And this is what chromatic aberration is. The light is broken up into the different wavelengths, and they're not brought to the same focus. So we get this sort of distracting artifact. And this is mostly with refracting telescopes, cheaper ones. And the way to combat this is to, in the early days, several hundred years ago, they came up with the idea of using two different types of glass in the lenses, crown glass at the front and flint glass at the back. And they made an achromatic lens. And what this does, here we can see the star and the lights being again broken up into component parts. The blue light's brought nicely to the focal plane, so it's nice and sharp. And the red light is actually brought a lot closer to the blue light. So for some time, achromatic lenses, as in absence of chromatic aberration, were thought to be the bee's knees. But there's still quite a large amount of chromatic aberration with this system. So they don't fully correct for chromatic aberration. And then in more recent times, people have come up with these apochromatic systems. And this consists of even more lenses in the system. Here we've got the starlight coming in, it's being refracted, and now you can see the blue and red light are much more closely aligned and coming to focus. So apochromatic systems generally can be regarded as having minimal chromatic aberration. If you look hard enough, you would probably find some, because it's just the nature of the lenses. And all these additional lenses are acting to have a different effect on different wavelengths of light. And so when people talk about doublets, triplets for refractors, they're talking about the number of elements in this system. So doublets has 2, triplets 3, quintuplets, I can't remember, quin something more. So how do we get rid of chromatic aberration? Well, don't use an achromatic telescope. So the cheaper refractors will be referred to as achromatic. They're not fully achromatic. They still show a fair amount of chromatic aberration. So if you want to do serious imaging and observing, you need an apochromatic telescope. Longer focal lengths, so refractors f12 and above, probably f10 and above, even f7 and above, the chromatic aberration will be less severe. You can buy additional optics. I haven't got a picture of one here. An Apochromatic Corrector, which will plug in into the focus tube of the refractor and help to correct the bending of the light to make it appear nicer and more focused at the same point. So the next thing we're going to talk about is Comatic Aberration, or Coma as it's more commonly called. And this again, primarily reflecting telescopes, but affects other systems to an extent. Here we've got a parabolic mirror, because now we're thinking about modern telescopes, modern reflectors. They've got primarily parabolic mirrors. And here is the optical axis. So this is where the light, this is light hitting the center of the mirror at right angles. And if light, these colors are just different parts of the target rather than different wavelengths. If light path is parallel to this optical axis with the parabolic mirror, then we've already seen that that light will all be reflected nicely to a point on the focal plane, and the observer will get a nice sharp image. Now the issue in coma is when you've got a target which is emitting light, and the light is hitting the mirror off that central axis, and that is when coma comes into play or becomes problematic. So if the light's coming in at parallel to the optical axis, it's not a problem. It's where the light comes in obliquely to that axis. And here we can see, I've just, again, this is grossly exaggerated. The green beam is being reflected and nicely comes to a focus on the focal plane. The yellow is very close to that, but the blue, because it's a long way off the other two, is actually being reflected, and where it's crossing the focal plane is a long way from this sharper image. And to more easily show how this poses a problem, I'm going to think about using a lens to represent it. It just makes it easier to show where the various light paths are going. So again, we've got parallel beams of light coming in obliquely to this lens, and here's the focal plane. And what happens is the lens is bending all these paths of light to a slightly different extent, and where they all merge is actually not on the focal plane. At the focal plane, where the observer is looking, there's a mishmash of what's happening. there seems to be an accumulation of a large portion of the light rays here, and then down here they spread out a bit. And if we think how that might look, then we get a pattern like this. It's a bit like the spherical aberration, but they're not stacked on top of one another. They're sort of slid against each other. So we've got a tight concentration initially, which relates to a good number of the rays coming to a focus. But then as we move away from that, we're getting these larger, fainter concentric circles, which are these more distal rays of light. And if we looked at an image, we would see something like this. The very center of the field of view would be nice and sharp. And as you get further away from the center and nearer the peripheries, further away from that optical axis, the coma gets worse. So coma is typically worse the further away it is from the center of the field of view. And in fact, we've got, I asked this chap if I could use his image from the internet, and he was kindly said I could. So here we have, I'm not sure what the target actually is. It's just to show that the impact of coma. So near the center, we've got these stars which look reasonably tight and sharp and pretty pin-like. But as we move away, they're looks like lots of little comets. These are not lots of comets. That would be a fascinating picture if it was. They're all stars, but they're suffering from coma, from chromatic aberration. The further away they get from the central axis. And again, here we've got the what spherical aberration is like. It's a very similar problem, but it's on axis. They're all stacked on top of one another. And then here we've got coma, where we've got central peak, central tight bit of star, and then it drifts away and becomes fainter because it's becoming more out of focus and the light spread over a bigger area, so that disc gets fainter. So fixing coma, well, don't use parabolic mirrors would be the simple answer, but then we don't want to use spherical mirrors because they give you spherical aberration. So you have to use something called a Coma Corrector, and very similar to the corrector for the chromatic aberration. A Coma Corrector would plug into the focuser and then aim to reduce the amount of distortion at the peripheries of that field. And for reflecting telescopes, these are typically in the order of just under £200. Coma is much less problematic with refractors and SCTs and Maxitovs, but it is a feature if you look hard enough. Now, the next thing to think about is something called astigmatism. My optician always says when I've got an astigmatism, and I always ask what it means, and he says your eye's shaped like a rugby ball. And I've never really understood this. And now I've actually, having researched this, I've got a much better idea. So there are two main causes, principally, of astigmatism. One is imperfect optics, and the other is a malalignment of otherwise good optics. If your kit is well aligned and you've still got astigmatism, then it's probably you've got imperfect optics. But if you've got astigmatism, you're not sure which of these two it is in the first instance. And I think this is a video. Yes, it's a video. So here we've got a lens and we've got a star, and the star's emitting light. I'm not sure, is the video playing? Is the video playing? It's impossible to tell. We'll soon see. I think it's playing. It's impossible to tell. But yes, it's playing. Don't panic. So we've got a lens, starlight's coming in. It's being refracted and brought to a focus. Oh yeah, here we go. Now what I've done in 3D Paint is make a lens. It looks like a giant Smartie. It's got two convex surfaces, and it looks pretty uniform. But for the purposes of this exercise, we're going to imagine it's got a very subtle defect. Now, the star's coming in, the star's on the left again, and the light rays are coming in through the telescope, hitting the lens. Here we can see lovely 3D Paint. I've discovered this software. It's very easy to use and quite powerful. So the light rays come in, they're being refracted by the lens and being brought to a focus. You can see the light rays are focused there. And when I recorded this, I've clearly gone mad with the swizzling around to show off the 3D effects. But what happens if we put another set of light rays at right angles to these two? So here's the original two. And now we've got another pair at right angles to those. Now, if this lens is slightly imperfect, it's slightly thicker here than there, what will happen if you just look from one angle, it looks like everything's brought to the same focus, which is fine. But when we swizzle it around, because the lens is very slightly different, although everything's coming to focus on the focal plane nicely, the position at which it actually achieves focus on the focal plane is ever so slightly different, because the lens, let's say, is thicker at the edges than it is on these edges. So light from different parts of the object, irrespective of wavelength, are achieving focus nicely, but in a slightly different position. And we can show that here. So here we've got perfect optics without any astigmatism, and you can see these concentric, the airy disc. And in astigmatism, we've got this effect. We've got a similar pattern, but instead of a sharp center, we've actually now going to have two centers that are merged together. And this is the rugby ball. This is kind of the effect of the lens being a bit like a rugby ball. It gives us this artifact of rugby ball shape. And here again is an illustration of the impact that the slightly imperfect lens might have. Now, if you've got astigmatism, if it's your eyes, like mine, then you should wear your glasses to observe, because that will make the image sharper, because your own glasses are correcting for the astigmatism in your eye. And then, so if you take your glasses off and you think your scope's got astigmatism, just make sure it's not you and you're fiddling with your optics for no reason. And the other thing is to check that the optics are perfectly aligned, so make sure the system is well collimated and focused. And it might be that doing that resolves the issue with astigmatism. If it doesn't, then there's probably something wrong with the optics, and most of the time I think we could live with it, but if it's really severe, you may need to think about getting it solved. Now, distortion is the last thing we're going to talk about. This isn't to do with image sharpness. The other aberrations are mostly to do with how sharp the image looks to the eye or when you image. This is more to do, or this is to do with distortion of the image scale and how the image is projected. So here we've got a box. We're imagining this is the star or the target that is the observer's looking at. And what happens is the light from the target goes through the lens, it's refracted and inverted because you get an upside down image, but actually the proportions are the same. So in an ideal system, you wouldn't see any distortion. But there are two main types of distortion. One is called barrel distortion. So this is where, again, the image looks nice and crisp and sharp and focused, but the image has been distorted. And in this situation, it's like it's being stretched over a ball. And then the other version is called pincushion distortion, where it's as though it's being pulled away from you from a central point. So here we have the native normal image. Here we've got the barrel distortion, and here we've got the pincushion. And reading, there's in fact one called a moustache distortion, which is a combination of these two. Now, on the whole, this isn't a problem for observing. People generally don't notice this issue. But if you've got a star here and a star here in the field of view, and you want to measure the distance between them, then this distortion become a problem. Here we can see the same two stars there and there. I've just measured these on the screen in millimeters, and you can see in the native image it's 41, and in this it's 64, which is a significant difference. And then in this one, the stars appear much closer. So if you're doing precise astrometry, and you're trying to work out the distance of stars in a given field of view, if you've got distortion, then that is problematic. So it's unlikely to impact on imaging, on visual, but if you're doing precise measurements, it could be a problem, but you can generally correct this with by digital methods from a digital data. Now, I lied and said this was the last topic. I've just seen we've also got pinched optics. This is nothing to do with thieves. No optics were stolen in the preparation of this talk. It's to do with the fixings or mountings of mirrors and lenses. And here you can see the primary mirror of a reflecting telescope, and it's held by these three clips, retaining clips, to stop it dropping, to stop the mirror moving, in effect, when you move the scope. And what happens if those retaining clips are too tight, it can distort the optics, and that's true of mirrors and of lenses. And obviously, if you've got 3 retaining clips, you would have a distortion like this. If there was 5 or 4, it would correspond to that. And again, Michael Lockwood, who has got lots of information on the internet about aberrations, allowed me to use this image, and he said if you've got good focus and good collimation, and you've got triangular distortion, he says it's pinched optics. And the solution to that is to work out which part of the optics, or which whether it's specific lens or mirror or whatever's in your system, work out which one it is, and then carefully slacken those. But you need to be careful, otherwise if you slacken it too much, something's going to drop out, and then you've got a broken optic rather than just a slightly pinched one. So I've rambled on far too long. I've used 3 very good books and some lovely resources online. And at that, other topics, I was going to talk about all of these things, but we just don't have time tonight. So you'll have to tune in another time for something on collimation, atmospheric dispersion, local seeing conditions, and thermal currents. And on that note, I'm definitely going to hand over now to Leigh. Thank you, Leigh.
Hi, welcome to the second part on aberrations. I'm going to talk about issues in astrophotography. The 2 main topics I'm going to cover, the first being optical problems and the second sensor issues. The first optical issue I'll deal with is vignetting. This is usually a lack of light hitting the periphery of the sensor. This is an effect that can be useful in standard photography, but can ruin an astronomical image. This is a very simplified diagram of the light travelling through the telescope to the sensor on the right. You can see there is a wide nose piece connecting the scope to the camera, and this does not impede the path of the light. In this diagram there is a narrow nose piece. This is impeding the light at the edges and will cause vignetting. The effects of this are obvious in this flat field test. In the image on the left, a 1.25 nose piece is used and has caused significant vignetting. On the right, a 2-inch nose piece does not cause the effect. These images show vignetting. Data is lost at the edges. All is not entirely lost, and I'll explain later how this can be overcome. The second optical issue is field curvature. Petzval field curvature is an aberration where light cannot be focused onto a flat plane. Most telescopes are designed to focus light onto the eye. Here you can see a basic diagram of a human eye. Our retina is curved. However, a camera sensor is flat, and this diagram shows the problem. Light travelling in the centre of the plane is unaffected, but the light travelling from the periphery cannot be focused on the flat plane of the sensor. This will cause the periphery of the image to be unfocused. The usual way to correct this is to use a field flattener. This sits in the light path before the filters or the sensor and corrects for the curvature. They do need to be positioned at a specific distance from the sensor, so the correct spacers must be used. There are telescopes that are designed with sensor use in mind, such as Celestron's Edge HD. These project a flattened field as default. Dust bunnies are bits of dust that get on the optical path, on a lens, mirror or filter, or on the sensor itself. This image has a dark area that is caused by dust on the filter. The way to resolve this is firstly to ensure your equipment is clean, but it's not going to be possible to remove all specks of dust, so we can use flats to correct for them. A flat file is taken either before or after imaging of a plain white field. You can use a glowing panel, a tablet, or even the side of a fridge. This will produce an image such as this one, which can be added to your stacking software to correct for the dark spots. As the flats can correct for dark spots in the image, they can also be used to correct for vignetting. The dark corners will be calibrated out when stacking. On the topic of calibration frames, there are two other types that can be used. Bias frames are required for dedicated astrophotography cameras. DSLRs and compact cameras automatically take a bias frame with every shot, so these aren't required to be done separately. In this image you can see the bands on the right hand side of the sensor. This is where the readout is done, and so the chip is slightly warmer and has picked up higher values. To compensate for this, we can take a number of bias frames so that we calibrate this extra heat out of the image when stacking. Dark frames are used to reduce the inherent noise in the sensor. These are taken with the lens cover on for the same duration as the exposure of the normal light gathering frames. The resulting image shows up the noise, which can again be calibrated out of the data during stacking, resulting in a better image. You'll also notice hot pixels in a dark frame. These are damaged pixels that always read 100% full. Cold pixels are similar but always read at 0%. Again, the stacking software will calibrate these out, replacing them with interpolated data from nearby pixels. Another sensor issue you may face is saturation. Here is an image of M42 I took when I first started out with astrophotography. You can see here the core is blown out, all the data is lost as the brightness from the central stars has washed out the detail. It's very easy to do this on targets with a wide dynamic range of brightness. M31 is another example of this. This can be compensated for by taking shots of different duration and stacking them together to produce a HDR or high dynamic range image, such as this one. This frame shows a large amount of banding, which can be a problem with sensors reading data from bright detail and dark backgrounds. There are a number of causes of this. Sometimes it is the way the camera reads the data from the chip and is inherent to the design of the camera. The camera's own amplifier can cause this, especially as the ISO is increased. Calibration frames should remove this problem. However, faulty cables and other electrical interference can cause this noise to occur and should be checked for. Grainy images are another problem that astrophotographers face. There are a few reasons for this. Using a higher ISO will increase the amount of noise visible in the image. Light pollution will also reduce the dynamic range of the image, forcing you to stretch it further. The main reason, however, is lack of data. You can see here the difference between 2 hours of gathering hydrogen alpha light and 11 hours. More data is always better up to the point of diminishing returns. Not so much a physical problem, but a cosmetic one for most astrophotography, are diffraction spikes. Some people like the cross effect produced by the vanes on Newtonian telescopes. Some even go as far as putting string across the aperture of refractors or adding them in with software. I think this one is mostly a matter of taste. A problem faced by users of alt-azimuth mount is that of field rotation. As the sky appears to move during the course of the day and night, the angle at which the image of an object is presented also changes. Equatorial mounts are designed to deal with this, but alt-azimuth mounts cannot. Imaging over a longer period, an equatorial mount follows the angle of the object. An alt-az mount holds the same angle. If imaging, this means that the edges of the image change, and the object within the frame will rotate. This will cause a degradation of the image size and quality. Equatorial mounts are superior for imaging, at the cost of increased price and higher complexity. Right, that's all for now. We will cover other topics such as mechanical errors on another night. Hopefully some questions, so please do shout up if there's anything else you'd like to discuss.
Right, thank you, Leigh. And that was good. The dust bunnies and stuff are always a pain, and had a member recently send in some images he was struggling with, and there was a lot of dust bunnies. So I've suggested have a look at the sensor and see how grubby it is, and blow some dust off and see if that makes any difference. That was for solar imaging, but I've not heard back from him. So oh, I can see Herbal's in the chat. Herbal, have you had any, let us know in the chat if you've had any luck with the cleaning the sensor. Have we got any questions? Lorraine says, hi from Northumberland, been some fabulous dark skies lately. Yes, it's been, had some here as well, Lorraine, cold nights and frozen cars in the morning. Brendan liked the bit of mooning. Yeah, we all like to see Richard mooning. What else? That's it. And Shirley was happy to see the moon. Thank you. Here's one for you then, Leigh. Julian said, when you say diminishing returns with more data, what's a good rule of thumb? And maybe for other people, can you expand a bit on what you mean by diminishing returns?
Yeah, sure. So the first few subs you'll get will obviously start to show you an image. And as I said, the more data is always better, but there is a point where more data doesn't actually add that much onto the image. So with a decent length sub, the sort of, if you took 5, you should get like a decent beginning of an image. If you take 10, you will improve it quite a lot. You'll start to lower the noise and start to iron out, a lot of the other defects in the image. When you get up to sort of 20 subs, you're probably going to start getting quite a good quality astrophotograph, really. Start to get on from 30, it's not going to get that much better. And again, 40, 50 isn't really going to improve the image at that point. There's a point where it does peak. And it does vary from setup to setup. There's no golden rule that says, right, this number of subs will give you an exact, fantastic image. And it does depend on the target and on the conditions. But roughly, if you can take sort of 20 subs, that will help.
Okay. And does the length of the subs make a difference? If you're only able to do, say, 30-second subs.
So yeah. So if I was probably thinking of like long duration subs. So
Okay.
I'm thinking of if you're using something like a long exposure CCD or CMOS. If you were say doing stuff like 5 minute, if you're doing galaxies with a color camera, you'd probably be doing 5-minute subs. If you were doing narrow band, you might be doing half an hour subs. If you're using a shorter duration, you still want to get the more subs the better, really. And you could look at it in minutes as well. So there was an image I showed earlier, I think I got about 11 hours worth, and that's going to get you a fairly good image with long exposures, and you can factor that down. So if you're doing galaxy photography, you could say 6 hours would probably get you a tremendous image for most things.
Okay, so that's a lot of 30-second subs.
It is indeed, yeah.
And for a common question is, you've got data for 11 hours. How do you collect that in one night in the UK?
You can't really, not realistically. There's going to be, only the dead of winter is going to allow you to do that, and having a very favourable aspect on the sky. If you're positioned in a flat field where you can take photos all night, you may be able to get that in. But just stacking allows you to collect data over a couple of nights. So take as long as you want, really. If you're taking deep sky, then it doesn't really change. The sky is fairly fixed on that scale. It's only planetary and lunar that tends to change that rapidly, and you need to collect all your data in a much shorter space of time.
So what do you do then about dust bunnies over 2 different nights?
Right, yeah, so really you should collect flat frames on every night, because there is the potential that you could get new dust on the outer optics. If you able to, and if you had to disassemble your equipment at all, then there's a chance that you can get dust ingress inside the equipment as well. So you should do flats for every session.
Right. And what about the bias frames? Are they fixed between sessions or?
Bias, yeah. So if you've got something like a CCD, you can do bias probably every 6 months. The sensor doesn't change that much. It's recommended you change them every now and again, but you can you can do what's called a super bias. So you take, say, 30 bias frames, you can stack those frames together, and then every time you run your image stacking, you can use that one super bias frame then, and use that to iron out any aberrations on the sensor.
And what about dark frames? How often would you do those?
Again, they should be done every time, because they're to iron out the noise on the sensor, and that could change every night. Temperature is a big factor in noise. So if you're using a DSLR, for instance, the temperature on different nights could be completely different. So definitely worth taking every time. You can fudge it and try and get away without it, but it's always better you get a better result if you do it every time. It just takes a lot. It does take up a lot of time to do that.
Yeah. And are the flat frames temperature dependent?
Potentially, yes. So you should really do the flats in the same session.
Okay.
You don't have to, and I've done it and got reasonable results without doing that.
We'll have to do a session on calibration frames, because I'm still never sure about flats. The flats I always do are awful. They're either too bright or too dark.
Yeah, so if you've got a DSLR, there's if you switch on the histogram function on the back of the camera, you can ideally you try and adjust the exposure so you hit roughly the middle of the histogram.
Okay, 50%.
Yeah, roughly that. Yeah. So it does depend camera to camera. Sometimes it's better to do a little bit lower, sometimes a bit higher. yeah, it does vary between device, but that'll put you in the right ballpark.
Yeah. Right then. Oh, Herbal's got back. It has worked, James, and I have just taken some photos of the sun and can see a sunspot. That's good. So, Herbal, make sure you share that image with Roy for the journal, if you're happy, and some information about the kit you used and things. And I'm glad cleaning has helped with those dust bunnies. Shirley, brilliant explanations there, James and Leigh. I've been trying to understand all of that stuff while attempting to focus my scope a while ago. Yeah, focus is a tricky one, and all these other bits are tricky. So it's just a part of the learning curve, Shirley. You'll fix one problem and then realise there's something else there to get your head round. But let us know what you're stuck on, anyone, and we can try and put on session for that. Herbal, can I ask what objects you would use the IR UV cut filters? So for planetary imaging, we generally use a UV and an IR cut filter. So we cut out all the ultraviolet part of the spectrum and cut out all the UV, so we're just getting the visible part of the spectrum, and that keeps the image a bit crisper because the other ends of the spectrum might still be sensed by the chip in the camera, but because of the different wavelengths, they can focus at a slightly different place and cause blurring. And also different features on the planets may appear under different wavelengths. So some features you see in visible light might not be seen in infrared light, but new features in infrared light might appear. So to avoid that confusion, people generally image planets with either just visible light, and people now do imaging of just infrared light. So they're going for the wavelengths above 650 or 700. That gives you much less light, but actually can give you a crisper image. And people lately have been doing that with the moon, imaging the moon with filters which just let through infrared light. The sensors seem most sensitive to infrared rather than the UV, I believe. So cutting out the infrared seems to be more important. Any other objects, Leigh, that we would use UV and IR cut filters?
Yeah, I mean, I suppose it's anything that's bright in IR, really. If you're using it for deep space, it's not such a big problem. But you can. Sometimes worth cutting out IR if you think the source is going to be bright. Some stars can get blown out if there's a lot of IR coming through, especially with sensors that are unfiltered. If it's something like a mono CCD or CMOS camera, there's zero filter on those, so they let everything in and display everything they see.
Yeah.
So yeah, definitely worth filtering it. It cuts down a lot. UV can cut down on haze as well. So sometimes you get slight haze to images. If you've got a UV filter, that can cut down some of the haze.
Well, I remember seeing something about reindeers and electricity lines. Did you show me that, Leigh?
I believe so. Yeah, I think in winter they gain
wavelength
the ability.
Was it?
Oh, it's quite short wavelengths. They get frightened by pylons in the winter because as the light drops, they gain the ability to see ultraviolet.
Right.
And then they can see the coronal discharge from pylons, and it spooks them.
Right.
So.
There you are. So if you've keep reindeers, keep them away from the pylons. I can see Richard's doing something with the moon in the background. The big C to the bottom left is Mare Crisium, which is one of the first, well, it is the first mare to see in a new moon. So the image is a bit, it's flipped. Yeah, it's flipped, so it should be the other way. If Richard can find the flip button and flip it left, right, in the horizontal plane, it'll be a bit more logical for my brain.
Yeah, I've just nipped back to my machine. Sorry, the image isn't very good. Unfortunately, the moon's now straight over Leigh's house. Sorry, Leigh, your house is causing the shimmer, I think. the
Leigh, turn your heating off.
Yeah, it's giving us a bit of shimmer.
Yeah, so no, that's a lovely. How old's the moon, Richard?
I'm not sure how many days. It's about 12% illuminated, I think, at the moment.
Yeah, 11.7%. My stellarium saying 3.3 days old.
Yeah, 3.3 days. Yeah.
It was looking lovely last night, and there were some various pictures on the internet posted. People taking images of the moon. So, Julian, in general, are refractors more prone to aberration, or reflectors, or is it equal? Well, they get different aberrations. So the reflectors generally suffer with coma. That seems to be the biggest issue for reflectors. Chromatic aberration is less of a problem. Spherical aberration these days is less of a problem if you've got a more modern scope. So refractors is usually coma and maybe some field curvature. The diffraction spikes, because you've got the spider holding the secondary. Some refractors have issue with in focus for imaging. So if you put a DSLR on a refractor, it depends which. Yours is okay, isn't it, Leigh, with the DSLR?
Yeah, with an ED80, yeah.
No, I meant the reflector. Sorry.
Oh, the reflector. Yes, I can actually get a reflect. Yeah, I've got a fairly short tube Newtonian that works quite well.
And then the refractors, the common issues are chromatic aberration, and again the field curvature for imaging, and dewing up depending on the temperature. So whatever kit you buy, you're going to encounter aberrations. So just do your research and decide what sort of astronomy you want to do. Is it visual? Is it imaging? We get several questions to the society on a monthly basis saying what telescope should I buy, or should I buy my husband, or whatever. And it's a very difficult one to answer, because one telescope seldom does everything. If you want to do everything well, then you probably need more than one telescope. So yeah, horses for courses. I'm not going to say any more. Stuart's thankful, grateful, interesting talk. John, faster scope gives shorter subs, better for tracking. Faster scope means more sensitive to collimation and aberrations. What's optimum? Yeah, so we didn't talk tonight about the speed of the optics. So talk about f10, f5, f3. So the lower the number, the faster the speed of the optics is. It's a bit of a contentious area, but the lower the number, if you're imaging, the more photons you seem to place on the sensor in a concentrated pattern. So you accumulate data quicker. So if you've got limited ability to track, then ideally you want a faster telescope. But as John says, if you've got a very fast telescope, then they're more prone to needing very precise collimation, and they can easily come out of collimation. So again, it's
I think the optimum is how much pain you decide you can put up with. There is a system called the Hyperstar and Faststar, which can turn a SCT into a F2 astrograph. So you're collecting a lot of light with that, but they are very prone to any problems. If they're slightly out of collimation, it's going to really ruin your field of view on there. And I think it's more of what you'll put up with, really. Some people are quite happy to be tweaking the scope every night before the image. Some people, want something they can just walk up to and use.
Yeah, and I guess it for astrophotography, people often say the mount is the most important thing. So it depends how good your tracking is. If you can accurately track and guide for 10 minutes, that's different from if you can only manage 20 seconds. So it depends what your target is. If you're going for planets, it's not really a problem, or the moon, or the sun, or most solar system targets, comets, asteroids. The tracking isn't that important. But if you're after deep sky targets, then you really do want the longest exposures possible on the whole. Richard's got the moon back again, that's good. He still hasn't flipped it. I can't remember where the flipping option is. You'll have a look round and find it.
That's why I've not flipped it. I can't find it.
Oh, yeah, go down.
That's the bottom.
Go up. Okay.
I'm sure it's in camera controls, I think. I can't find it.
Someone might comment. So, where did we get to? David Turner, were the images Leigh showed all real colour, or were any false colour images?
I think most of them are either, if they were the colour ones, most of them were real colour. So, taken with a DSLR. The black and white ones, I think most of those were taken with the hydrogen alpha filter. So they were on a mono camera with the hydrogen alpha filter. The one right at the start with the Flaming Star Nebula, that one is a blend of colour data and hydrogen alpha. So that it's a very hydrogen alpha rich target. So I used the hydrogen alpha as a channel. Boosted up the red on that just to bring the detail out.
Yeah, so some of those images, embarrassingly, I sent to you with that I'd taken. I think, yeah, they're all real colour. The ones that I sent.
Oh, the vignetting.
Yeah.
Yes.
Awful. Rob Bush. Could the Schmidt ghost halo be due to poor baffle tube flocking? Rob's still got trouble with his Schmidt ghost halo. Rob, you meant to send me the images. Baffle tube flocking. Well, there are no baffles in a Schmidt Cassegrain. What does he mean, Leigh, by baffle tube flocking?
I'm not sure, to be honest. Is this halos on images or with an eyepiece?
Images, I think.
Right. Okay.
I think we need to see them, Rob. And you need to remind us again if this is with imaging or with eyepiece as well. And also if this is related to bright objects, and certainly let us know if there's any moon or street lights visible, because they can often project light in from the side and cause trouble.
That's something I didn't mention on the talk was it could be there's a phenomena in CMOS sensors called oh, hold on, remind myself. So CCDs often suffer from smearing, where you get a bright object can cause a trail down the lines of the pixels.
Yeah.
The other there's a similar phenomenon with CMOS where you can get let me just find out the
Not blooming.
Blooming, yes, that's it. So if you've got a very bright object, that the photons from that object are hitting the pixels on the CMOS, and it can actually overexcite the chip, and the electrons in the pixel wells actually spill out into the surrounding pixels, and that causes a phenomenon called blooming. So it's like the light that's not actually there, and you get an overspill of light coming from a highly saturated area.
Herbal says thanks. That's good. Rob, has anyone else seen a faint halo on bright stars with an SCT? Rob, if you at your computer, can you send us an image and we can try and get it up and have a look at that?
There we go. It's just sent us an update, both eyepiece and camera.
No street lights in view. Okay. Yeah, be helpful to see that. John says, don't forget the length of the time spent in the cold. Yes. But ideally, you just want to set an imaging run off and leave it for an hour or so, and then have a cup of tea and come back. So all SCTs and Macs have a baffle tube on the center. Right, okay. So yeah, talking about the central draw tube in the middle. I don't know. I honestly don't know that about if that's a problem with that. We'll have to see the image. But Richard's doing well with that low moon, and you can see the shimmering from the local seeing problems from heat from Leigh's roof.
It's coming and going, isn't it? It's a good example of lucky imaging, isn't it? You do see, well, particularly directly on the computer that's taking the image, there's some very sharp images there that just not lasting very long.
It's looking nice and sharp now. I think if you could capture that, that would be nice. Again, we can see a lovely terminator between day and night on the moon, and the cusps going off top and bottom.
Yeah, I wasn't sure that it all fit on the chip with the ED80, but it's just on. Well, the illuminated part is anyway.
What camera are you using?
It's the QHY 5. It's the mono one.
That's lovely. So, have we got anything else? Looking around. No. So, I think that's it. Thank you, Leigh. Thank you, Richard, for doing some lunar imaging for us. So that's it, Plumtree, for another month. Well, not sure what next month is yet, but we'll work it out and let you know. So again, thanks, Leigh. Thanks, Richard. I'll hand over to Richard.
Good stuff. Yeah, well, thanks very much both. It's really good. Again, huge amount of work going into putting those on. So thanks very much. Next meeting, when are we? May soon. 6th of May, Thursday, 6th of May, and that is Martin Braddock, and that's on Extremophiles, Why There Must Be Life Elsewhere in the Universe. So it'd be nice if we get some on Mars with a new rover beforehand. That'll make it more interesting. So join us for that, 8 p.m, usual place on YouTube, Thursday the 6th of May. As James said, we're not decided on the plum tree one yet, so we'll let you know in due course what's planned for that. Membership, we make the plum tree meetings freely available on YouTube, so if there's anyone watching who isn't a member and would like to join, then you're most welcome too. So that's the membership rates on the screen. So just head over to the Nottingham Astronomical Society website, and all the details are on there of how to join. Most welcome you if you're interested and like what you see from our online meetings. Hopefully it won't be too long before we can get back face to face. We're definitely now going to target the annual barbecue, hopefully at the observatory. I think that's on, so look, on the 7th of August, Saturday the 7th of August. So that we'll definitely want to get that one as a reunion of members back. If not before then, we'll see how things go over the next couple of months or so. Right, that's about it for us tonight. I hope you enjoyed the evening. We'll see you for the May meeting with Dr. Martin Braddock on Extremophiles. But from myself, James and Leigh, have a very good evening. Good night.